Joel Hirschi is the Associate Head of the Marine Systems Modeling Group at the National Oceanography Center in the UK. He became head of the group in 2018, but has been with the team for over a decade. He has been highly involved with the AMOC in his professional career, having served as a postdoc at the University of Southampton to do model-based pilot studies that underpinned the original RAPID proposal in 2004. After his postdoc, he served as a research fellow within the RAPID 26 North project. So today he is here to present a summary of the paper that he led as part of the AGU special collection entitled The Atlantic Meridional Overturning Circulation and High Resolution Models. We are very happy to have you here today, Joel. Please go ahead when you are ready.
Thank you very much, Jenny, for the introduction and for the opportunity to present our review. At this stage, I also would like to thank all my co-authors for all the contributions, ideas, and data that I have provided that fed into that review. So this review is about the AMOC in high-resolution models. And to be able to run such models, one needs very powerful computers. And therefore, I thought it might be useful to have an overview of how much the computer power has increased over the last 60 or so years. This is what is indicated by the blue line. And so it's the units are in a petaflops, so 10 to the power of 15 floating point operations per second. And during that 60 years, since 1961, there has been a staggering increase by an order of magnitude of 12. So it's so this line really refers to the peak performance of the most powerful HPC system, a high-performance computing system currently available. And but still, so that's just to give an idea of how staggering that development has been in the last 60 years. And in the following, I'd like to mark a few milestones on that plot, milestones in terms of modeling or also in terms of AMOC. And to start, I thought it was good to start with the Stommel 1961 model, which is a box model and that can be solved analytically, no need for powerful computers there, but it raised very interesting questions about the AMOC bistability that are still being pursued to this day. So we still don't know for certain whether the AMOC is bistable or not in nature. And even the most powerful models cannot give a definite answer to that. They can give clues, but no definite answers. So a very inspirational little model for many subsequent studies that have happened over the decades. Next, I'd like to mention the code developing by Brian and Cox, and that came out in the late 1960s. So this really was the start of a kind of a more modern modeling of the ocean. So this is already quite a refined ocean general circulation model that was then used as a template for many models after that, and the influence of that are still felt nowadays. Next, I thought when I wrote that review, I was wondering when the first simulations that were actually able, which we would refer to as high resolution, how far back that goes. So by high resolution, I mean simulations that are able to represent some of the mesoscale in the ocean. And I was actually quite surprised and, to be honest, quite humbled to find that Sentinel and Mintz had produced a regional model of the Gulf Stream region that was already not resolving, but representing some of the mesoscale features there. So that's actually quite impressive, more than 40 years ago. And again, so a little bit humbling, to be honest. And the next one, I thought that would be, there is a nice, very nice study that what came out in the mid-1980s by Frank Bryan, who used a full general ocean circulation model, actually based on the Bryan and Cox code, to illustrate that some of the concepts that Stommel had highlighted in his box model could be reproduced in a more realistic, much more realistic and physically complete setup therefore providing some confidence that this is something that may be happening in the real and may be possible in the real world. Now, moving on, the first global simulation that was eddying, that was by Sempner, and this time Chervin in the late 1980s. A simulation I didn't know about before I started writing that review, but again, quite impressive. It's a global model. They refer to it as eddying. The resolution, however, is only 1/2 of a degree, so it's really in the equatorial region that we start to see some eddy-like features around the tropical instability waves, but certainly this is a resolution that it would not be sufficient to reproduce features like mesoscale ocean eddies at mid-latitudes, for example. Then moving on into the 1990s and early 2000s, then there have been really, that's a period characterized by major developments, various efforts, various places in Europe, in the US, in Japan, to produce high resolution models that reproduce the ocean mesoscales. Some of these models are regional, some of them are global. That time period also coincides with some rewriting of the models to be able to make them usable on machines that were becoming more and more multi-processor at the time, and that's an evolution that is still going on up to this day. Now, the final bit is really the last 15 or so years where there has been a consolidation of these efforts, and with models becoming more refined, more established at higher resolution, HPC computing power being sufficient to do longer simulations covering many decades or sometimes 100 and more years. Some of these models are even coupled, some of them are ocean only. The resolutions are typically in the order of 1/10 of a degree, 1/10 or 1/12 of a degree, perhaps a little bit more, up to 1/16 of a degree in some instances. That's pretty much where we stand at the moment. Now, before moving on to the some AMOC results, I thought it would be useful to give you an idea of what such a current model, I would say state-of-the-art, pretty much top of the range model looks like. So this is from a coupled model where a 1/12 of a degree ocean model, the NEMO model, was coupled to the UK Met Office atmosphere, and that model has been run for about 100 years. And we can see how the incredible level of detail it can reproduce in the ocean, lots of mesoscale activity, ubiquity of eddies, and in this case it's a coupled model, so we see lots of obviously the activity in the atmosphere. The atmosphere has a resolution of is also eddy resolving, so it's a 1/4 of a degree atmosphere, so both elements, both components, ocean and atmosphere, pretty highly resolved. And so this is the type of tool that we now have at our disposal to try to understand and make progress on our understanding of the AMOC. Now, this looks quite beautiful, but do we actually learn something from it? And that's what the next part of the talk is going to be about. So this plot is a slide is quite crowded, and I don't expect you to take in all the details. What it shows is the Atlantic Meridional Overturning circulation in depth coordinates, in Z coordinates, a subset for a set of high resolution models ranging from a 1/20th a degree here on the top left corner down to a 1/4 of a degree here. And for comparison, I thought it would be useful to add a few circulations that we find in lower resolution models. That means models that are not non-eddying, that cannot reproduce ocean eddies. So what is quite apparent from that plot is that there is a wide range of solutions. Some models are stronger than others. The shape of the overturning cell can vary. Some cells are deeper than others. Some are rather shallow. However, what is quite interesting is that there's a tendency for the high resolution models to produce an AMOC that is more vigorous. That is most clearly seen when we got a suite of resolutions like the ones highlighted here in red. So these are 3 simulations at 1/12, 1/4, and 1 degree that are run with the same model, with the same atmospheric conditions, and keeping everything as similar as possible. And so what is quite clear is that we get the strong circulation at higher resolution and something quite a bit weaker at low resolution. And that is true for different types of models where this sort of hierarchy of resolutions is available, where there is no attempt is being made to optimize the model to have a strong AMOC, trying to keep all the conditions, all the settings as similar as possible as one can when increasing the resolution. And really what emerges is that there is a tendency to produce a stronger circulation, perhaps because of stronger AC interaction. This is not fully understood yet, but it's something that one can see, and have yet to see a high resolution model of 1/10 of a degree or better that simulates a weak AMOC circulation. This plot on the left is summarized here in this plot, in this panel on the right hand. And what it shows is the maximum AMOC as a function of latitude for the for either high resolution eddy-rich models, which is shown here in green, for eddy permitting, and for non-eddying models shown with the blue and with the red lines. And for comparison, we also added the AMOC from CMIP, from a large subset of the CMIP5 models. And what comes out of that is that one can reproduce a vigorous AMOC circulation with a low resolution model as well. But as said before, CMIP5 was quite tuned. So lots of tuning went into that to get an AMOC that was satisfactory for the 2 hierarchies I mentioned before. This is not the case. So no attempt of optimization was made in that respect. However, there is still an interesting difference in terms, if you compare CMIP5 with the high resolution models, there is a tailing off of the strength of the overturning at the high resolution at north of about 30 or so degrees north, which is not seen at the low resolution. And this points to a potentially interesting difference in how low and high resolution models reproduce the AMOC. And that's the bit I'd like to explain a little bit more in the following. So this slide here shows the AMOC in Z coordinates for 2 high resolution models, so eddy-rich models, one at 1/20 degree Viking model from the Kiel group, 1/10 of a degree here from the Access model from Australian group, and compared with their lower resolution counterpart at 2 degrees and 1 degrees. So what becomes quite visible is again this drop in the strength of the AMOC if you look at the northern part, let's say north of around 30-35 north, at the high resolution, which is not really seen at low resolution. The overall circulation is weaker, yes, but it does tend to extend a bit further north, and it's really at the very northern end of this overturning cell that there is a marked decrease in the overturning cell. So whereas the sinking seems to occur over a wide range of latitudes and the high resolution models, it tends to be confined on a much narrower band of latitudes in the low resolution models. The middle panels show the overturning stream function in density coordinates, and here we see interesting differences as well. First, we see that the maximum of the overturning occurs further north than for the overturning in Z coordinates. That is true for the high resolution and for the low resolution models. We do expect that because both the overturning part, so the vertical circulation, as well as the horizontal, the gyre circulation, can both project onto the AMOC and therefore can lead to a higher value than if you just look at the AMOC, at the overturning component on its own. This is made even more clear in the lower panel that shows the maximum overturning as a function of latitude for the overturning in density coordinates shown by the black line, and the one in Z coordinates shown by the blue line. And what is quite obvious here is that there is a difference. So the black line, so the AMOC in density coordinates is higher than in Z coordinates in all instances, but that difference is much less pronounced at low resolution than at high resolution. And this is not only the case for the two models that are illustrated here, but that seems to be the case as well for the models that were used by, for example, by Gökhan Danabasoglu for his review of lower resolution models that he looked at a few years ago. So what tends to happen is that it's illustrated by these schematics here on the left. So high resolution models could be symbolized by this pronounced loop at the northern end of that North Atlantic circulation that highlights that there is a pronounced expression of the gyre onto the AMOC. To some extent, the picture is the same at low resolution, but here that northernmost bit linked to the gyre is much less pronounced. And so the low resolution model is somewhere in between what we see in high resolution and what we had if you look at a simple box model or a two-dimensional model that would have a circulation that it can be symbolically represented by the schematic at the bottom left here. Now, what that all points to is that there must be a difference in the subpolar gyre, because these are the latitudes where we see these marked differences between high and low resolution. And what this panel here illustrates is that there is a much stronger subpolar gyre circulation. So this, by the way, shows the barotropic stream function for high resolution eddy-rich models in the top row, and low resolution models the bottom row, and a comparison with an observation-derived barotropic stream function that came out a few years ago. Some nice work by Colin de Verdière and Oli Trot. So what is quite clear from that plot is that the subpolar gyre is much stronger, much more pronounced at high resolution than it is at low resolution. And also the shape of the subpolar gyre is much more comparable to what the observational estimate would suggest. So it's quite so with a gyre circulation of that type, one can quite easily imagine that this would project quite strongly on the overturning circulation in density coordinates, and much less so for the low resolution models. So essentially what happens when moving to high resolution is that the strength of the subpolar gyre is consistently quite strong, there is variability, but it typically varies between around 35 and 55 or so sphere drops. And again, I have yet to see an example of a high resolution model that simulates a weak overturning, a weak horizontal gyre circular subpolar gyre like the one we see here or the one we see here. So of all the models I've looked at, I haven't seen any example of that. And so compared to a plot that I took from a paper by Gökhan Danabasoglu, is that there has been a shift in the strength as to where the strength of the subpolar gyre and of the gyre circulation in general, the subtropical and the subpolar gyres, where they cluster at high resolution compared to where they were at low resolution. So the gyre circulation, I didn't say much about that, but the same to some extent is also true for the subtropical gyre that has a much stronger recirculation close to the western boundary, something we do not really see at low resolution, but something that observations do suggest exists in the real ocean. Now, this points to an interesting difference in terms of the pathways of the AMOC, but there are also very marked differences in terms of variability in what can be reproduced in high resolution models compared to their low resolution counterparts. This slide here shows that the mesoscale in an ocean model, when it is subject to small perturbations, is going to start to diverge. This is illustrated here for a 6-member ensemble that was done with the NEMO 1/12 pedigree model, where we use the same atmospheric conditions but apply little perturbations at the beginning of year 2009 that lead to a gradual decorrelation of the eddy field. And that decorrelation is not just seen in the eddy field as such, but can then feed into other components of the ocean circulation, as shown here for the Florida Strait transport, which start to diverge after a couple of months. Not much happens for the first 3 or so months, but then it starts to diverge, and the correlation between the different ensemble members decreases. And this is not just seen for currents like the Florida's current or the Gulf Stream, but then also projects on the AMOC, as illustrated here. So you see the AMOC gradually gently starting to diverge, and then more and more as we move on with these ensemble members. And this panel here at the bottom left shows the same, but just as deviations from the ensemble mean, just to highlight the divergence a bit more clearly. And so this is something that is really specific and is actually quite useful, because this is a sort of variability that if you measure in the real ocean, you can't get rid of. It's something that you will have in whatever observations you make. You will be subject to that sort of noise, and high resolution models do help to quantify how big that impact could be, therefore how much noise there may be in the observation, and how much is maybe the signal that you're really interested in, and how much might be due to these mesoscale processes and other processes that are chaotic or intrinsic in the ocean. Now, this already brings me to my final slide, where I'd like to give an overview and a summary of aspects of the AMOC variability, and finish with a few words as to where we feel that high resolution models could be very useful in the next few years. So what this plot here, I need to explain that a little bit. It shows the maximum variability of the AMOC when computed in a depth in Z coordinates. It shows how the maximum variability that is found between 30 south and 60 north, how that changes as we look at different time scales. So with time scales ranging from 4 hours here to daily here, to 5-day averages here, to monthly averages here, to annual averages here, and to 10 years averages here. The blue line is the average AMOC that is found over the range of 30 south to 30 to 60 north. So that would be basically a line following, broadly following the line I'm tracing with my cursor now. And the bottom red line shows the same as the red line, but for the lowest value that is observed, the lowest standard deviation that is observed for the AMOC on these different time scales over the same range of latitudes. So what is striking about this plot is that how large the variability actually is. If you look at at short time scales, the average AMOC that I discussed before is typically in the order of broadly between 15 and 23 drops. And that average value happens on a background of AMOC variability that is actually much, much larger. That can be many times that value. So standard deviations of up to 53 drops are possible. That's around the equator. And this is something that is really more pronounced in high resolution models than in low resolution models. And this is something that is found not just at the equator, but we got a pretty large variability going all the way to mid-latitudes that are much, much larger than, for example, the variability that is suggested that we find, for example, in the rapid observations. By the way, I should have mentioned that before, rapid observations from 26 north, the variability on different time scales, 5 daily, month, 10 days, monthly, for 100 days for different time scales is given here by the green arrows. So it falls well within the range that the model is producing. So now, what is quite interesting is that this very high frequency variability is really concentrated on the shorter time scales. If you look at, if you compute the variability using monthly means, it's essentially gone, as is shown here in this panel on the left, on the right. And that is something that is certainly to keep in mind when one is studying the AMOC. Really, that the values that are often mentioned in the literature, they happen on a highly variable background. However, what is very unclear at this stage is how important this high frequency variability is. It has only been seen in models so far. There are no observations in nature, in the real ocean, that can confirm the presence or absence of a variability like the one we see here. We know that in the model, it happens for very clear physical reasons. There has been a recent nice set of papers that just came out by Blaker et al. And by Bell et al. That explain why there is this variability at the equator. But what we don't know, not even in the model, is whether that actually matters, whether this has whether there is a climatic relevance to it. or whether this is just water that is being sloshed around on very short timescales, but not being really climatically active, that is something that we do not yet know. And this is what I wanted to illustrate a bit with that schematic here at the bottom left that shows, suggests what the potential climatic relevance could be on different timescales, ranging from the shortest timescales to the very longest ones of many, many years or thousands of years. One could perhaps assume that the importance is less on on shorter timescales than it is on the longer timescales, where it is well established that the AMOC can have a major impact on the climate and weather, or at least on the North Atlantic region and beyond. But this is not clear that the same is true for shorter timescales. However, the uncertainty is large. The shorter timescales could feed into the background of the ocean via impact on mixing. So it's not inconceivable that the mean state we observe is partly set by what happens on these very shortest timescales. And this essentially brings me to the end of that talk. And what I'd like to say is that where we could really ideally use these models quite easily with our really wonderful tools is to try to understand what these high resolution variability, what it actually does, because you don't need to run them for a very long time to see whether it's doing something or not, because for the coming years, we will still not be able to run these models on a multi-centennial or multi-millennial years for ice age cycles. That is still going to be beyond what we can do, let's say, for the next 10 or so years at least, I would imagine. So there's a lot of interesting things that one can be done on shorter timescales. And so it's just like to draw the attention that this is something that might be of interest as well, and where we got fantastic tools to investigate it. And that's where I'd like to conclude, and I'd like to thank you all for your attention.
Thank you, Joel. So I see on the timer we're 3 minutes over, but if it's okay with you, we'll take the next 10 minutes for Q&A.
That's absolutely fine.
All right, perfect. So a reminder for those who have a question for Joel to use the raise your hand button. Otherwise, you can type your question into the chat box. So with that, I'll start with a question that was in the chat box that was sent to me by Rick Williams. He says, "Hi, Joel. Congratulations on a very nice talk. The overturning involves water sinking. Can you express the change in overturning with resolution in terms of where the sinking takes place?"
Let me go back to that slide. That's the one you're referring to, Rick. So let me go, okay. If you look at the shape of the overturning, so I haven't looked specifically at the sinking itself, but that should be implicit into the shape of the overturning cell. So if we see where the overturning decreases, where we see tight isolines, like here, for example, between 30 and around 30 north and 50 north, and then here, that's where we got most of the sinking. And here it seems to be a more gradual thing. So we see equally spaced isolines from around 30-ish north all the way to 60 north, which suggests that the sinking would be quite similar over a wider range of latitudes. So that's what I wanted to highlight with these arrows. Yeah. Whereas here, for the low resolution, the overturning cell almost look like they are being cut off with a knife, and the isolines are very tight within a very narrow band of latitude. So I would say that is indicative that the sinking is happening in that rather, most of the sinking is occurring in that relatively restricted band of latitudes.
Yes. So I guess my point, Joel, is whether that was the mechanism which was dictating in many ways the different structures that you see. So that high resolution, maybe the sinking is happening near side boundaries or sloping boundaries, and at higher resolution, there's a different character to the sinking than at coarser resolution.
There has been some nice work there by Sieben Dreifout and colleagues who showed that a lot of sinking does tend to occur along the rim of the subpolar gyre. So, and that's something that is, so it's not something I went into any details here because for question of time, but there is there definitely is some work that suggests that this is along the rim of the subpolar gyre that that there is an enhanced sinking. Now, exactly why this is happening, I can't give you the mechanism, but that's what the model suggests.
So I think Mike Spall's on the call, but Mike's did a paper on that in the Labrador Sea in a more idealized setting. I think it's a nice way of thinking about things. Thanks very much.
Okay. And speaking of Mike Spall, I do see his hand is raised. Go ahead.
Yeah. So can you tell if the changes are due to having narrower and faster boundary currents or shedding of mesoscale eddies from the boundary currents? Can you hear me?
Yeah. I get your question. Yeah. So certainly, I would imagine. I mean, the strengthening of the subpolar gyre circulation, I would certainly partly attribute to the strengthening of the western boundary currents. What we can also see is that there's also a barotropization of the current in at high resolution that is more pronounced at high resolution at low resolution. So that's so if you look at the structure of some of these currents, there is quite a much more pronounced barotropic component than what we see at low resolution. So whether the shedding of eddies, what impact the shedding of eddy has, I do not know. Potentially, and potentially that brings the right water of the right properties into the center of the Labrador Sea, and therefore exposes that to a cold atmosphere and enhances convection in that part. But I'm speculating, so I'm not sure whether this is what's happening.
All right. I have a question in the chat by Harold Feldman. Would it be helpful to have more optimized software? If so, whom could I contact on that topic?
More optimized software. Cannot be specified a bit.
Harold, if you want to unmute yourself, go ahead.
Unmute. That works probably.
Yes,
can you hear me?
Yes.
Okay, great, thanks. I'm thinking about optimizing for GPU usage or otherwise.
Oh, yes. Yes. Well, absolutely. I mean, if I go back to the very beginning of, if I look at that HPC plot, so we are on the verge of having exascale machines. So 400 petaflops is the strongest. And the current codes, as you will undoubtedly know, are far away from being able to exploit these type of machines. And so being able to run them on GPUs, and there are various efforts going there, for example, going on there. I know at MIT, also ETH Zurich have done quite a lot of work on that and have some promising results. So absolutely, I think, and there are quite a few efforts going into that, into be able to running on GPU, but more generally, at the moment, scalability of these models is not very good if we go beyond a few tens of thousands of processors. That's already a lot, but the most powerful machines have millions of processors. If we were to try to run one of these models using 1 million processors, we would gain absolutely nothing, quite the contrary, because everything would be eaten up by communication between processors. And yes, absolutely, that's definitely something that where effort should be go into. Otherwise, we just won't be able to exploit exascale machines in the way that we ought to.
Do you have any contacts for me? If you could put that in the chat, maybe.
I will do that. Yes, I'm more than happy to. Yeah, that would be great. Thank you.
Okay, great. Thanks.
All right. Do we have any final questions for Joel before we wrap this up? All right. Question from Stuart Cunningham. Go ahead.
Hi, Joel. Nice to see you. I guess my question is, do you think there's any modern observations that can actually differentiate between, say, the 1/20th and 1/10th degree in terms of, realism?
Sorry, can you repeat that, Stuart? Because I mean, you were cut off right in the middle of the question. Sorry.
Okay. So I was wondering, you talked in broad scale about the differences between the 1/10th and the 1/20th of a degree models. And I was wondering what ocean observations you might imagine that could help you distinguish which were more realistic.
I don't think I said that much about the 1/10th and the 1/20th. So I think I would put both of them into the same category. I mean, they're both they're both, I would say, we call them eddy rich, and 1/20th is probably just about eddy resolving in the Labradors, in the subpolar gyre region, whereas 1/10th probably would not. Now, I mean,
Mike Spall hinted at the importance of trying to decide about, the role of eddies or the role of boundary currents, for example.
Yes, I mean, certainly, yes. So I am not sure which observations would be the best to I mean, clearly what we can see, I think, from satellite observations is that there are eddies peeling off from western currents into the interior of the subpolar gyre. Most of the high-resolution models that I've shown today do not do that. Some of them do, but the majority of them do not really do it very well. So there's certainly something that these models are one of the many things that they're not good at. I mean, none of these models, by the way, are good at reproducing overflows, for example. So the overflows is still something that has even our very nice 1/12th degree, the coupled one that I've shown you, the overflow is not overflows are not satisfactory, far from it. And all these models still have a problem that they produce too deep a mixed layer in the Labrador Sea compared as to what observations suggest. So, however, so I suspect, I mean, the observations that, for example, are done in a OSNAP, obviously fantastic to validate or invalidate what the models are doing. I mean, there's still a large discrepancy between even the high-resolution models in terms of how strong the subpolar gyre is. They're all on the strong side, but some of them may actually do even too much of a good thing. So to have a good observational estimate of the strength of the subpolar gyre over a longer period of time is certainly something that would be a very useful thing to have.
Thank you.
I think that should wrap up our AMOC webinar for today. So thank you again, Joel, for your presentation.
Welcome. Thank you for the attention.
And then thank you also to all the participants that are on the line today. Our next webinar will be on May 20th. So we're skipping April and heading right into May 20th for a talk by Helen Johnson on the recent contributions of theory to our understanding of the AMOC. So I'll see you at that point. I'll send out an email reminder and everything. And the recording for today's talk will be available by early next week. So thank you, everyone.